issues of antibiotic resistance. She also wants to uncover from the very beginning of life itself how ribosomes first came into being and started creating proteins. It sounds ambitious, but for the Ada, discovering the origin of life is just next in the series of Mount Everest. She is indeed a living inspiration to all of us. Her name echoes the essence of service, dedication, and compassion. It is an honor to have a great personality like you with us, ma'am. Your journey has shown us how a small, fragile breeze can become unconquerable storm and will always have an everlasting impact on the world. Thank you, ma'am. Thanks for accepting our invitation.
It was a difficult task to summarize Madam's journey in such a smart manner. Thank you, Priyanka. May I now request Dr. Ved Prakash Mishra to kindly felicitate Professor Ada Yanar with our Indian tradition of shawl, shriftwear and memento as a token of respect and gratitude for being with us today. Thank you, sir. I am profusely elated to take an opportunity to humbly invite Professor Ada Yanar to enlighten the gathering and to grace the stage.
Hello. Shall I say ladies and gentlemen or fellow researchers? I prefer the second. And it's a great honor for me to speak to you. All professional physicians, medical-oriented chemistry, and biophysics. I think I don't have to explain what ribosome is and why is it important. I think that you all know this. And in my opinion, you all know how it works, how it reads the genetic code that is brought to it by messenger RNA, and how it creates peptide bonds in the newly born protein from the amino acids that are brought by the tRNA and operate or combine within a pocket in the ribosome that is called PTC, peptidine transferase center, which is also made of RNA. Here, ribosomal RNA. So actually, we go into a world of RNA functioning molecules. And the longest one and the most frequent one is the ribosomal RNA. So ribosomes in all living cells, they are doing the same thing, producing peptide bonds, producing proteins according to the genetic interactions in the messenger RNA, function the same way, although their main structural elements are the same, but the size is becoming larger with evolution. So when we determine the structures of the ribosomes, the first structures, we went into second mission that we had to understand how antibiotics can stop them. Because ribosomes are so important for life, almost half of the naturally made antibiotics are targeting them and paralyzing them. That's a huge amount of antibiotics, and they're all natural. What does it mean, natural? That among the many mutations that each particle in the body undergo constantly almost, those that were successful in disturbing the antibiotics became, those that were successful in disturbing the ribosome became antibiotics, and later on, when resistance started to show up, actually almost after the antibiotics started to be successful, the resistance became, not only started, but became more and more spread around the world, because more and more doctors, hospitals, and so on use the antibiotics against all types of disease, bacterial disease or infections. Then there became a need to get to treat the unwanted resistance, and also this was it tried to be successful by using the ribosome as the main framework where the antibiotic attack and the resistance to this attack happened. So this was the time that more or less we got the structures, we understood the structures, and immediately afterwards we understood how not all the antibiotics, but many of them work, and later on all of them. And we as scientists wanted mainly to fight the antibiotics, to fight the resistance against antibiotics. So as I say, the resistance, the natural resistance, is attempting to minimize or get rid of the antibiotic attack, the infectious attack by paralyzing their carriers. It means producing antibiotics. And nature has done fantastic antibiotics are natural. There is not much more to do in order to make them better, and the companies did it all, almost immediately when the useful antibiotics went into practice. But there was resistance against it. Resistance became more important than what the companies made. And now we are again in a situation that resistance is frightening. It's very powerful, and it grows much faster than human beings can fight it. So the World Health Association, already 4 years ago, announced that they feel that within less than 20 years there will not be any antibiotic that will be useful. I'm not sure that they are right in 20 years, or some say 15 or 25 years, but it's soon. So we thought about our next attempts were looking for other ways to prepare antibiotics, to design antibiotics, to design the next generation antibiotics, where we can synthesize all of them. We can put all the chemical considerations into the synthesis, and we can try, actually put as a rule, to make them biodegradable. It means to minimize the contamination of nature. And for this reason, we determined the structure of several important infectious bacteria and looked for their specific and exposed and not existing anywhere else features on their periphery, on the outside. The periphery of ribosomes are made of proteins, ribosomal proteins, but also ribosomal RNA. And ribosomal RNA, like every other RNA, can be targeted by antisense RNA or by other compounds that make double helical interactions with the RNA, like the DNA, RNA itself, but it means from the outside, or modified ones, the PNA. And we showed that we can stop the growth of each infectious bacteria by its own little adjusting adapters. So this is what we call next generation antibiotics. We can make them a fluorescent, so we can find out where the infection is if it is in the body. And we can make them penetrating, like the vaccine of Pfizer and Roberta that were made recently. So this was the next step. The step afterwards was to design them, and this is what we are doing now by identifying such features. While we were so much concentrated in the structure of ribosomes, we noticed that the position where the bonds are being made between the amino acids, the peptide bonds are being created, which is called the PTC, is embedded a pocket, universal pocket, which is of the same or almost the same structure in all ribosomes, from bacteria, from fish, from flowers, from elephants, from human beings. So it gave us the opinion that, supported the opinion that the ribosome evolved from these pockets, because these pockets are evolution independent. And if so, we thought maybe we can make the pre-ribosome piece, which we called the proto-ribosome. And at that point, we started to synthesize such pockets, and it took over 5 years until we got some constructs that look like the right pockets. But at that point, we more or less were stopped, not really stopped, but more or less, because we wanted to show that these pockets are functionally active. You can make peptide bonds. And this was really, really, really complicated. And if we talk about curiosity-driven science, this was one of the main points that we didn't give up on it. But then we were lucky that an Indian postdoc joined us. And I'm very happy and very proud of announcing her contribution. Her name is Dr. Tanaya Bose, and she was the only one, and the first and the only one at that time, to show that the proto-ribosome is really active in making peptide bonds. Not only this, she was able to show which type of proto-ribosomes are active, which are just being there, made there by chance, like evolution, and not useful, so they were kicked out. And these are those that are still functioning until today, until inside us in all ribosomes. So Dr. Tanaya Bose was able to not only to create, as I said earlier, but also to find not all the rules, but the main rules of which initial proto-ribosomes can be developed into the ribosomes. And I'm very proud of her results and very proud to be able to let you know that we really love and enjoy collaborating with Indian scientists. Actually, in my group there are two more Indian scientists. One is a doctor called Rajan, and one is still a student called Disha. Disha she knows everything, and she's really fantastic. And she's one of the main powers in another project that we are very much involved in, and these are genetic ribosomal diseases that we perform together with Dr. Hagit Yonat, who is sitting here. And we are trying to find out how these diseases are being created, and of course later on, how to look at them. So actually, 25% of the known cancers are related to modifications, mutations in ribosomes, in the ribosomes of the EPP. Also, an anemia, a very unpleasant, let's call it, anemia called DBA, that 91 different mutations are associated with it. And there is no knowledge whatsoever about these mutations, any mutation of the DBA or the cancer or other diseases. They are known in the genetic level, it means in the DNA. It was not shown yet that all of them, some of them are being expressed and disturb ribosome function. It was shown indirectly that some of them inhibit ribosome production because of the mutation. It's not known how yet, but this was already noticed. So we are trying now to understand the two sides. The side of not enough ribosomes because they were not created owing to the mutation, or ribosomes that were created but function wrongly. And that's what we are doing now with most of my group, but the main powers among the postdocs and students is Disha and Rayan against two Indians. So before I finish, I would like to know that by now I told you all what we are doing, published or unpublished, or not yet ready for publication, and that we appreciate very much the interaction